Hello YouTube. One of the most significant aspects of science is explanation. Science doesn't just involve making predictions, it also offers explanations of phenomena. And this has seemingly given us a very deep understanding of how the world works. Today we're going to examine in some detail what's involved in giving a scientific explanation. What criteria must good scientific explanations meet? So as a preliminary point, it's worth clarifying what is meant by explanation. The term explanation covers many different things. We can explain how to do things, such as how to drive a car or how to use a computer, or I might explain the meaning of an artwork. Scientific explanation, however, is concerned specifically with answers to why questions. We want to explain why things happen. Why did the dinosaurs go extinct at the Cretaceous-Tertiary boundary? Why is it that planetary orbits sweep out equal areas over equal intervals of time? Why was the Spanish flu of 1918 so much more deadly than other flu epidemics? So it's answers to why questions. So that's the general problem that we're going to be focused on. Now this video concerns scientific explanation, but we might want to keep in mind the question of, is there actually anything special about scientific explanation? After all, non-scientists also explain plenty of things. I might explain why Frank is angry by saying that his car has broken down, or I might explain why the cake didn't rise properly in the oven by saying that you used the wrong kind of flour. These look like perfectly adequate explanations, but they're not scientific explanations. Of course, we're going to focus specifically on the scientific case, but it's just, it's worth keeping in mind that maybe we want the theory of explanation to apply to non-scientific explanations as well. So today we're going to look at what's called the Deductive-Nomological model, which was proposed by Carl Hempel. In some ways this is maybe not a good place to start, because I think this model is actually quite counterintuitive. But this is really where serious philosophical analysis of scientific explanation begins, so we have to start here. Now, one of the most obvious features of many explanations is that they seem to cite a cause. Why did the dinosaurs go extinct? Because an asteroid hit the Earth. The asteroid caused the extinction of the dinosaurs. Now, Hempel was one of the major figures in the logical positivist movement. The logical positivists were strict empiricists. They believed that all knowledge is derived from sense experience, and this led to a general skepticism of causal claims. And this, of course, goes back to Hume. You're probably familiar with Hume's analysis of causation, but we'll just go through it very briefly. Consider one billiard ball hitting another billiard ball. We see the first billiard ball move, it hits the second, and the second starts moving. And what we would say is that the first ball striking the second ball causes the second ball to move. So what's going on here? What is this causation? We arrive at this conclusion because of a constant conjunction between the two types of events. Right? When you repeatedly observe one ball hitting another and then the second ball moving, you conclude that the first ball causes the movement of the second. So for x to cause y, it must be the case that x is regularly followed by y. There's a constant conjunction between x and y. But notice that this isn't all. Night is regularly followed by day, but night doesn't cause day. So additionally, causation involves what Hume calls a necessary connection between the two events. And this is a kind of metaphysical glue that binds the events together. The trouble is, we never observe this necessary connection. All you ever actually observe are regularities. You see one billiard ball moving and then you see the other ball moving. You don't see the connection between these two events. So necessary connection is not something you can sort of demonstrate through observation. But furthermore, we can't derive it logically. There's nothing contradictory about supposing that the first ball hits the second ball and then the second ball just does nothing. The second ball just doesn't react to the impact. So So this notion of necessary connection, where does it come from? It doesn't seem to be based on experience. It doesn't seem to be something we derive logically. And so for this reason, empiricists aren't really very happy with the idea of causation. And Hempel shared this skepticism. Causation itself is something that needs to be explained. We can't just take it as a primitive when we're trying to understand how science works. Another point to bear in mind is that empiricists tended to be anti-realist. So you can see my video on scientific realism. I've got a whole series on scientific realism if you're interested in this. But the point is that empiricists felt that ultimately all scientific claims can be expressed in terms of statements about immediate observation. So they were sceptical of any unobservable entities cited in any scientific explanation. For the empiricists, the point of science is prediction and control of observable phenomena. And statements about unobservable entities, so statements about electrons and protons and so on, these should be viewed as useful tools. They don't really describe the world beyond our experience. So this is an additional reason to worry about causal relations in explanations. If we shouldn't believe that electrons exist, well, obviously we shouldn't believe that they can cause anything. So in developing the deductive-nomological model, this is the kind of background. Hempel is going to try to avoid being committed to metaphysical ideas like causation. He's going to try to avoid being committed to the existence of unobservables and so on. Okay, so first of all, we need to go through a bit of terminology. We draw a distinction between the explanandum and the explanans, where the explanandum is a sentence describing what is being explained, and the explanans is the sentence that does the explaining. I ask, why did the dinosaurs go extinct at the Cretaceous-Tertiary boundary? Because the Earth was struck by a large asteroid. In this case, the extinction of the dinosaurs is the explanandum, and the asteroid impact and its effects is the explanans. The basic idea then of the deductive-nomological model is that explanation is a kind of argument. Specifically, to give an explanation of x is to show how to derive x from a logical argument. So the conclusion of the argument is the explanandum, and the premises are the explanans. And the argument must have a form that goes like this. So we have to have some premises stating the relevant laws of nature. Then we need some premises stating the initial conditions. And then from that, you derive the statement describing the explanandum. So I'll illustrate this with Hempel's example. If I put a sample of mercury in hot water, it expands. And we want to know, why is this? Why does a mercury expand? In giving an explanation of this, we need to state relevant natural laws. And so the law will be something like, all metals expand when heated. And then we state the initial conditions. So that's that the sample of mercury is placed in hot water and that mercury is a metal. And from this we can derive that the sample of mercury expanded. So we have an argument looking like this. From the statements of the natural law and the statements of the initial conditions, we deductively derive the explanandum. And of course, an important point here is that the natural law must actually be used in the deduction. It must be such that if the statement of the natural law were removed, you would no longer be able to derive the statement of the explanandum. So this needs to function as an essential part of the argument. And that of course is why this is called the deductive-nomological model. The reasoning is deductive, and nomological denotes things relating to laws. So we have the deductive-nomological model. So this is scientific explanation according to Hempel. Now, this might seem like a fairly minimal conception of explanation, but the point is that this shows us that given this law and given these initial conditions, we should have expected the mercury to expand. Hempel says that explanation is, and I quote, an argument to the effect that the phenomenon to be explained was to be expected in virtue of the explanatory facts. And of course, if you have these premises, then you would indeed expect the conclusion. And I think that this conception of explanation does make some sense. After all, we ask for explanations of events that are unexpected. When something surprises us, or when something seems unexpected, we want to know why it happened. We ask for an explanation. So a good explanation shows us that actually the event shouldn't have been unexpected. And so Hempel thinks that that's the function of explanation, and it does look like this model fits that. Now, one point that's very important to clarify here is this thing here, the law of nature. What is a law of nature? Hempel says that all scientific explanations must assert a law of nature, but the question of what a law of nature is a big debate, and it's certainly a very difficult concept for empiricists who are skeptical of metaphysical ideas like causation. So what can we say here? Well, first of all, a law of nature is going to involve some sort of universal regularity. All metals expand when heated. That's without exception. If you have a metal and you apply some heat, it expands. Now, actually, I should say that actually this is not true, because there are cases where metals will contract when heated. I'm obviously using a simplification for the purposes of illustration. There are more precise laws that do underlie the expansion of mercury, but just to keep things simple, we'll just say that all metals expand when heated. So the point is, we need in our explanation a law to pick out a universal regularity. However, there's a question about how to distinguish law-like universal regularities from merely accidental universal regularities. So consider all pieces of pure gold are less than 100,000 kilograms. Well, presumably that's universally true. There never has been and never will be a piece of gold with a mass greater than this. But we think that this is not a law. So what's the distinction here? Why doesn't this count as a law, but something like all metals expand when heated does? Well, the way that Hempel deals with this is to say that laws are those universal regularities that support counterfactual conditionals. And a counterfactual conditional is a statement of the form, if X had happened, then Y would have happened. We might have a sample of a metal that we never apply any heat to. Nevertheless, we could still say, if we had applied heat to this sample of metal, then it would have expanded. And this isn't the case with the gold example. In this case, the regularity doesn't support counterfactual conditionals. So think of a conditional like this. If two bodies of pure gold whose individual masses are more than 100,000 kilograms are put together, the resulting body will have a mass of pure gold less than 100,000 kilograms. Well, that's not true. In principle, there's no reason why we shouldn't, build a piece of pure gold heavier than 100,000 kilograms. So we don't get, this doesn't support the counterfactual conditional. Of course, there's a lot more that could be said on this point. The distinction between accidental regularities and laws has received a lot of philosophical discussion, and it's certainly questionable whether this can actually be worked out in a way that would be acceptable to an empiricist, especially given that there's no observable difference between a law and an accidental regularity. Appealing to counterfactuals is dodgy because we only observe the actual world. We don't observe counterfactual states of affairs. So this is certainly one place where we might try to attack Hempel's model. But assuming that we can give an acceptable analysis of natural law, we do have a nice simple model of explanation here. To answer the question, why did X happen? We show that X follows from a set of initial conditions plus laws governing those conditions. And Hempel adds a couple of additional requirements as well. So first of all, he says that all the premises of the argument must be empirically testable. We must be able to determine whether or not they're true or false, or at least we must be able to provide some sort of confirmation or disconfirmation through experiment. And that's a crucial requirement for an explanation to be scientific, because science is based on empirical testing. You perhaps could give an explanation where you had no way of testing the premises, but that would be non-scientific. Second, Hempel says that the premises must be true, at least as far as we know. So they have to be supported by the evidence. They have to be verified by the evidence. You don't give a good explanation by citing things that that you think are false. So let's take another example, just so we're all clear on how this works. Suppose we have a 5 kilogram object floating in space, and there are no net forces acting on it, and then we apply a force to it of 20 newtons, and the object accelerates at 4 meters per second squared. And we want to explain this acceleration. Why does it have this acceleration? Well, we use Newton's second law, that force is equal to mass times acceleration, and we can give an argument like this. Premise 1, x is a 5 kilogram object. Premise 2, force of 20 newtons is applied to x. Those are the initial conditions. Premise 3, force equals mass times acceleration. That's the law. So the conclusion is that x accelerates at 4 meters per second squared. More specifically, the derivation would look like this. You have a force of 20 newtons, that's 20 kilogram meters per second squared, and the mass is 5 kilograms, so you plug that into the formula. If you divide each side of this by 5 kilograms, then you get 4 meters per second squared is equal to the acceleration. So that's the explanation. Another example would be the derivation, the explanation of Kepler's laws by deriving them from Newtonian mechanics. Kepler's second law, for example, says that in its orbit around the Sun, a planet will sweep out an equal area in an equal period of time. So a planet moves faster when it's closer to the Sun than it does when it's further away. And we can derive Kepler's laws from the laws of Newtonian mechanics. We can show that given Newton's laws, and given the initial conditions of having a sun surrounded by planets, the planets will obey Kepler's laws, and that would be a deductive-nomological explanation of Kepler's laws. So this is quite a nice feature of the deductive-nomological model. It allows us to explain both specific events, such as this object accelerating at 4 meters per second squared, and it allows us to explain general laws, like Kepler's laws, general patterns. Okay, the deductive-nomological model has a rather interesting consequence, that explanation is essentially equivalent. It's fundamentally the same kind of thing as prediction. And this is because we can make the deduction either before or after the explanandum event has occurred. When we make the deduction before the explanandum event occurs, this is a prediction. So let's take an example. Let's say we observe the orbit of Neptune, and we say, why did Neptune take the path that it did? Why did it have that orbit? Well, then we use Newton's laws, and we use an initial position of Neptune at some earlier time, plus the influences of the other planets and so on, to derive Neptune's orbit. That's an explanation. But obviously, at that earlier time, we could have used those laws, plus the positions of the planets, to deduce the path that Neptune will take later. And that would be a prediction. So prediction and explanation are fundamentally the same. They differ only in terms of when the deductive argument is given. Recall Hempel's suggestion that giving an explanation of x is a matter of showing that x should have been expected on the basis of the laws and the initial conditions. So this is just to say that an explanation of x would have been a prediction of x if it had been given before x occurred. This is known as the Symmetry Thesis. Every explanation could have been a prediction, every prediction could have been an explanation. And of course that's appealing because it gives us a unified view of science, where these two things, which at least initially look like they're different, prediction and explanation, actually they have exactly the same logical structure. So I think that's a rather pleasing result.